right, so going back to this question, 22.26D, what I want to do, since we're just talking about diazotization in this section of chapter 22, I want to try to solve this problem and solve it by using diazotization chemistry. So using an aryl diazonium ion. Now, in terms of retrosynthesis here, I don't have a ton of space, but, for installing a carboxyl group, we can do that using Meyer chemistry, can't we? Because we know that we can install the nitrile, and we can install that from a diazonium ion, right? And we know that we can install that from an amine, and we know that we can install that from a nitro. So, the first step is going to be putting in a nitro after we have this group, because this group is an ortho-para director, okay? Whereas the nitro is a meta-director. So it makes sense that we would put in the tert-butyl group first. So how do we put in the tert-butyl group? Well, we'll use some Friedel-Crafts alkylation. We'll treat the benzene with tert-butyl chloride, and we'll use iron 3 chloride, and that will install the tert-butyl group. It's a really big, bulky alkyl group. And so when we go to install the nitro group using nitric acid followed by and sulfuric acid together, we're going to end up with the nitro para to that big giant tert-butyl group. So we've got our nitro group here. Now, in order to do some diazonium chemistry here, we're going to need to reduce that. So we're going to treat it with iron and acid, aqueous acid. And of course, that would make the anilinium, so we need to deprotonate that using sodium hydroxide. That gives us this compound. So now we've got the aniline derivative. Now I'm kind of running out of space here, aren't I? So let me see if I can move this guy up here, maybe. There we go. So this is my retrosynthesis up in the corner now. Okay, so now we're going to diazotize this. So we treat it with sodium nitrite and hydrochloric acid. We get the diazonium ion. So let's make that diazonium ion like this. Then we're going to treat it first with cuprous cyanide to install the nitrile, and then we hydrolyze that to the carboxylic acid by treating it with acid and cooking it up. And there you go, my friends. That's it for that synthesis. Again, are there other ways to do this chemistry? Sure, absolutely. You could use a Grignard, or you could use benzoic oxidation. That would work too. What I mean by benzoic oxidation is you could just make this compound here, okay? And since you have benzoic protons here, you could just oxidize that with the Jones reagent. That would work. Or you could make the bromo here, and then you could do a Grignard chemistry to install the carboxyl. That works too. So there's more than one way to do it for sure, with all the chemical knowledge that we have in chemistry 3111. But this is still a very good way of doing it, the method that I have laid out here, where we go through a diazonium ion. Well, there's another question that I had here in the slides that deals with the diazo compound, and this will probably be worth the value of maybe one multiple choice question on your next quiz. I've actually seen this question, or a question very similar to, where is it? This one here. I've seen a question very similar to this show up on the final exam. Okay, and it's not even asking you to design a synthesis or anything like that. All it's saying is identify the reactants. Just draw two molecules that you would put together to make this compound. So really, it's a diazonium, or a diazo compound, excuse me. You're making it via an Azo coupling reaction. But remember, the Azo coupling reaction, that you want to have the electron donating group on what's going to be your nucleophile, so this is going to be on your nucleophile, and then the electrophile is going to have the diazonium ion on it. So it's going to be the electron withdrawing or the electron accepting group, okay? The electrophile, we'll put electrophile, we'll say that's going to be the diazonium, okay? So the question is this then. I can either break the bond here and do my retrosynthesis from here, have the diazonium on this part with the amine, or I can break the bond here and have the diazonium over here. Could anybody tell me which bond I would break in my retrosynthesis? Would it be the red one or the blue one? It's going to be the blue one, absolutely, right? Because if I just have aniline by itself, right, aniline is strongly, has a strongly electron donating group on it. So this is my electron donating group, and therefore my nucleophile is just going to be aniline. So here's aniline, okay? And then the portion that's going to have my diazonium ion has two sulfonic acids, and sulfonic acids are electron withdrawing, right? So that's going to make an even more powerful electrophile. So we'll put here electron withdrawing groups as well. So that's going to look like this. I'm going to have my diazonium ion here. Okay, and then I'm going to have one sulfonic acid here and another one over here. Just like that. So what's my synthesis going to look like? Let's write it out. I would start with this compound, the nitro compound. Okay, or let's start it with the aniline derivative. That'll make it a little simpler. So I have my aniline derivative. Okay, I still haven't made my diazonium salt yet, so I'm going to treat it with sodium nitrite. And you're just going to treat it with the aniline in the second step. Okay. Yeah, so you're going to treat it with aniline in this step. And you could even practice drawing a mechanism for this if you want. You know, you could give it a shot. You could either draw the curved arrow. Well, I don't have the diazonium ion drawn, but anyhow, here you go. So, and that's going to give you your product like that. The whole section about heterocycles, it says to skip it. However, I think you should know a few heterocycles because they're just so ubiquitous in organic chemistry, especially for anybody who's interested in medicine. We see heterocycles all throughout, drugs. So it's a good idea to know, heterocycles like pyridine, which you probably already do know. This one here, this is called morpholine. So I'll write the structure here if you have something that looks like this. This is morpholine, okay? In the spectroscopy of amines, I'll just leave that as an FYI because these are all things that we would have covered already. We looked at the infrared spectra of primary and secondary amines in Organic Chemistry 1. We saw that primary amines give two NH stretch signals from symmetric and asymmetric stretching, whereas secondary amines only give one. Tertiary amines don't have any nitrogen-hydrogen bonds, so they don't produce that stretch in the 3,300 to 3,500 reciprocal centimeter range. The NMR spectra, the proton attached to a nitrogen, there's a really wide range that we see chemical shifts for those protons. Why? Because of, hydrogen bonding, concentrations of solvents, the different types of solvents, temperature. But basically, you get blurring and you get no splitting for those protons either. What else? And spectroscopy of amines, again, just talking about proton signals here and the deshielding effects of the nitrogen. And that's really it. We talked about alpha fragmentation for, compounds that have amines. We talked about the nitrogen rule and how when you have an odd number of nitrogens, you have an odd mass for your compound. But this is a really good slides here at the end. It goes over all the reactions that we covered in this chapter. So let's take a look. The first one is an old one, right? The first one is just taking an alkyl halide and treating it with a cyanide, which just does an SN2 reaction. And then you can reduce that nitrile to the primary amine using lithium aluminum hydride. But the thing is that you add a carbon, right? So adds one carbon to the structure. Whereas if you start with a carboxylic acid and you make a primary amide, and reduce it. You started with the same number of carbons, or you finish with the same number of carbons that you start out with. Making an amine on benzene, so making an aniline derivative, like is shown down here. I mean, we talked about this at length already in the class. The only thing that's really new is using the tin 2 chloride for reduction. So we talked about that a little bit. What else? We saw the azide synthesis. I talked about that already today, how we do that using sodium azide. We talked about the Gabriel synthesis and how to do that. Then we talked about reductive amination and how it's a great way to make primary, secondary, and tertiary amines. So very, very powerful chemistry, very useful chemistry. From there, we talked about acylation and when that is helpful to use the acyl as sort of a protecting group that mitigates the reactivity of the amine on an aromatic ring. We talked about Hofmann elimination and how you need these special conditions of excess iodomethane to do the exhaustive alkylation. Then you treat it with silver oxide, water, and heat to do that Hofmann elimination. And we explained why you get the Hofmann elimination. Then we talked about reactions with nitrous acid. We talked about making nitrosamines, which are carcinogenic compounds most of the time, so not the most useful chemistry. However, we talked about making diazonium salts or diazonium ions, which are very useful when we want to do Sand-Meyer reactions. And these 4 reactions, where we have the copper 1 salts of bromide, chloride, iodide, and cyanide, these are the Sand-Meyer reactions. The CHEM reaction is not a Sand-Meyer reaction. It's just a reaction of a diazonium salt. So we talked about using hydrofluoroboric acid to install a fluorine. Then we talked about a couple other reactions of aryl diazonium salts, treating it with water and heat to make a phenol, treating it with hypophosphorous acid to just install a proton. Just repeat those reactions. And then the last thing we talked about was Azo coupling, right? You want to have an activating group on your nucleophile, and then you take your nitro, which you could convert to an amine, and then convert to a diazonium ion. And there you go. You do an azo compound, and you make these wonderful, colorful compounds, which are of interest probably in the food industry and the clothing industry as well. So something kind of interesting there. And that covers all of the chemistry for chapter 22.